Okay, so in this video, what we're going to talk about is how to write a Lewis structure. Now, there's about 4 main rules that we use. So what I'm going to do is go over those rules first, then we'll try them out on some compounds. All right, so here's the first one. So the first direction that we're given is that we need to write a skeletal structure where the electronegative atom goes in the center. Okay. And then we draw a bond, which again, remember, a bond is 2 electrons between neighboring atoms. Okay. Second step, we then count the total number of valence electrons present. Number 3, we draw a single bond between the central atom and each of the surrounding atoms. And then number 4 says this: all of the outside atoms must follow the octet rule. Okay. And if the central atom does not have enough for octet, then we use a lone pair to form a double bond or a triple bond, depending on the situation. All right, so let me go through the set of rules again. We write a skeletal structure where the electronegative atom goes in the center. And then we draw a bond between neighboring atoms. So this usually, to make a little note about what we're doing here, the electronegative atom that goes in the center, usually this is going to be the atom that forms the most bonds. Okay. So usually that atom goes in the center. Okay. Now, another thing I want to point out is that sometimes you have to use the rules in you're not going to go step 1, step 2, step 3, step 4. Sometimes, actually, I'm going to be honest, most of the time, I count the electrons first. I usually deal with the electrons first because that way when I start drawing a structure and start putting electrons in, I know exactly how many electrons I'm dealing with. Okay. So I usually will go steps 1, 2, and 3. I'm going to do in some sort of order. Usually I go 2 first, then write a structure, then put the electrons in, and then see where I'm at. Okay. All right, so let's try a compound out. First compound we're going to try is CS2 carbon disulfide. All right, so when I'm being asked to draw the Lewis structure for this molecule, first thing I want to do is count up how many electrons are we dealing with. So let's do that. So for carbon, we know that there's one carbon atom in this molecule, and that since carbon's in family 4A, it's going to have 4 valence electrons. So carbon's going to contribute 4 electrons to the molecule. Sulfur, we got 2 atoms here, and sulfur is in family 6A, so it's going to have 6 valence electrons. So 2 times 6 gives me 12. So if I add those together up, I should have 16 valence electrons. Nice. So that I already know pretty much how I'm going to, how many electrons I got to deal with. Okay. Now, I want to draw a skeleton structure. So I have to figure out which atom's going to go in the middle. Now, since sulfur is in family 6A, it wants to make 2 bonds in order to get to 8. Carbon's in family 4A, it wants to make 4 bonds in order to get to 8. I'm going to put the carbon in the middle. Okay. Now, one thing I want to point out is that sometimes you will start drawing a Lewis structure and it may not work, and that's okay. That's part of the process. So one of the things that we're going to talk about later on in this video and also in the next video is how do you evaluate one of these? How do you know if you're right or not? But anyhow, let's get back to this. So we're going to try this first one. We're going to try to put carbon in the middle because it wants to accept 4 bonds. We'll put sulfur on either side. Okay. All right, so we got carbon in the middle, sulfur on either side. So now what I'm going to do before we do anything, I'm going to draw a bond between carbon and each of the sulfurs. So that's going to use up 4 electrons already. So we're at 16 electrons. We used up 4, so we've got 12 electrons left. Okay. Next, what I want to do is make sure that each of the outside atoms is following the octet rule. So that means I've got to put in the lone pair electrons. So starting with the sulfur on the left, I'm going to put in my lone pairs. So that's 2, 4, 6, 8, 10, 12. All right. So I've used up all of my electrons. All right. So now, finally, we have to make sure that the central atom is following octet. So the outside ones are definitely, there's 3 lone pairs and 1 bond, so that gives you 8 valence electrons, so we're good on that. The sulfur on the right, same deal, 3 lone pairs, 1 bond, so that's 8 valence electrons, we're good here. Carbon's got no lone pairs and 2 bonds, it needs 2 more. So the way that we're going to have to make carbon happy is to take one of the lone pairs from sulfur and use that to form a double bond. Okay, I'm going to do likewise to the other sulfur. I'm going to take one of the other lone pairs and also make that into a double bond. So now you have something like this. Carbon is going to be double bonded to sulfur. Okay, carbon's going to have another double bond to another sulfur. Okay, now look at what just happened. You have 2 lone pairs on the sulfur on the left, okay, and 2 bonds. So remember, two electrons are in each bond, so that means 4 electrons are bonding. You've got 4 electrons in lone pairs, so sulfur still has 8 electrons, so it's good. Sulfur on the right, 2 bonds, 4 electrons, and then you've got 2 lone pairs, another 4 electrons, so sulfur's got 8 valence electrons. It's happy. Carbon has 2 double bonds. So that means 4 times 2 gives you 8. Carbon now is happy. So the final structure, the final Lewis structure is this, that you have carbon in the middle, sulfurs on either end. Each sulfur is going to have 2 lone pairs, and carbon is going to be involved in 2 double bonds with each of the sulfurs. Okay, so the next Lewis structure that we're going to try is formic acid. Formic acid has this molecular formula. You're going to start with an H, and then a C, and then another O, another O, and an H. Okay, or the molecular formula would be C, CO2, H2. Something like that. All right, so again, let's follow the pattern that we just did in the last segment. Let's do it again. So now, first up, let's count up how many electrons we've got. So we got, excuse me, we got another carbon here. So we got 1 carbon atom times how many valence electrons? We got 4 electrons per carbon because it's in family 4A. So 4 electrons total. Oxygens. We've got 2 oxygens here. Each oxygen has 6 valence electrons. 2 times 6 gives us 12. We're good there. Hydrogen. Hydrogen, we got 2 hydrogens, and each hydrogen brings over 1 electron, so that means 1 times 2 gives us 2. So if we add all that up, 4 plus 12 gives you 16, plus 2, 18 electrons. So that's how many electrons we're dealing with for this compound. All right, next step. We're going to try to put we're going to try to arrange these atoms in such a way that we can start making bonds. All right, so let's try this out. I'm going to put the H connected to the C, and I'm going to connect the O. Let's make this into a line. HCOOH. We're going to space it out like that. Are we right or wrong? Let's find out. So what I'm going to do, so now I've got my structure. Okay. What I'm going to do is put a bond between each of these atoms. So that gives us 2, 4, 6, 8 electrons. So 18 minus 8 gives us 10 electrons to work with. Okay. All right, so we got 10 electrons left. Third thing, let's make sure that each of the outside atoms have octet first. So let's the hydrogens, because they only want 2 electrons. Hydrogens are happy already, so that's awesome. Let's start with the oxygens. The oxygen on the right has 2 bonds, so it's already got 4 electrons. So that means I need to put in 2 lone pairs to get it to another 4. So that would give us 8 valence electrons total. All right, so we've used up 4 electrons, so we've got 6 electrons left. Let's work on the oxygen on the left. Okay, same deal. It's in 2 bonds. I'm going to put in 2 more electrons. Okay, so I'm going to use up 2 more electron pairs, so I'm going to use up 4 electrons. Now we got 2 electrons left over. All right, so now carbon. Okay, so I'm going to put in the 2 electrons that we got left over. Okay, so that uses up the 2, that uses up all of our valence electrons. We're good. All right, so now carbon isn't happy because carbon's got 2 bonds, which means that's 4 electrons, plus the lone pair, which means you got 6 electrons, so carbon's still missing an electron pair. Okay, so what if we try what we did the last time? What if we take a lone pair from the neighboring oxygen and use that to form a double bond? So here's what we got. Carbon, double bond to an oxygen, okay, connected single bond to another oxygen, connected to a hydrogen. So this is a possibility. So at this point, this structure that we have is a potential Lewis structure. It's following the octet rule. Okay. Now we haven't talked about how to evaluate a Lewis structure yet. So right now, that is a potential solution to the Lewis structure. Now, there are a couple problems with this structure. And to talk about that, I've got to actually define something else. All right, so we had a potential solution to that Lewis structure. So again, just to remind us what that Lewis structure was, it looked like this. Okay, so now we want to know, is this the true Lewis structure, or is this not a good structure? How do we know? Now, to answer that question, we got to take a look at something called formal charge. So let's talk about this a little bit. Formal charge. What formal charge is, this is the electrical charge difference between the valence electrons in an isolated atom and the number of electrons assigned to that atom in the Lewis structure. Excuse me, so there's going to be a little bit of writing, I apologize. So this is the electrical charge difference between the valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. All right. So how this works, we count up the number of non-bonding electrons. In other words, these are lone pair electrons. Okay. So we count up the number of non-bonding electrons. We count half of the number of bonding electrons to that atom. Once we have that, we can use this equation where formal charge is going to be equal to the number of valence electrons in a free atom minus, and I'm going to put this in brackets, the number of non-bonding electrons, so your lone pairs, minus half of the bonding electrons. Okay. All right. Now, some things to keep in mind about formal charge. Here's the biggie. Oh, sorry. I don't know what that is for, but let's go down here. Some guidelines to keep in mind. So the biggie here is that the sum of the formal charges of all the atoms must equal the charge of the molecule or ion. Okay. So that's a biggie. All these formal charges have to equal the sum, have to equal whatever that thing is. So in this case, for the formal charge of formic acid, this was neutral. So when we add up all these formal charges for this Lewis structure, it better be 0. Otherwise, we got a problem. All right. So second rule. Structures with small formal charges, like a +1, -1, like that, are preferred over ones with large formal charges. So if you are going to assign a formal charge to an atom, you want to make sure that you keep it small. Okay. Number 3, place negative charges on electronegative atoms. So this is also another really important thing. If you're going to place a negative charge, you better put it on an atom that can accept a negative charge. Okay. So, that being said, let's go back to the structure. All right. Now, hydrogens were okay because remember, they have two electrons. They're good. Now, let's start with the carbon. Let's move from left to right. The carbon was the first one that we kind of had a little bit of interest in. So let's calculate the formal charge of carbon. So the number of valence electrons in a free atom is 4 electrons. Okay, because carbon's in family 4A. So we're going to take 4 electrons minus. In this case, for carbon, how many non-bonding electrons does carbon have? Well, in this case, you've got 2 non-bonding electrons. So I'm going to write 2 electrons up here. Now, how many bonding electrons do you have? You've got the double bond, which is 4, plus the single bond, which is another 2, so that gives us 6. Half of that is going to be 3. So I'm going to write half of 6. All right. So already we know that half of 6 is going to be 3 electrons. So everything inside this bracket, 2 plus 3, that should be 5. Okay. So that means 4, we have that 4 electrons minus 5. The charge in carbon is going to be a -1. So that means that the carbon is going to carry a -1 charge. So that's carbon does not necessarily want to carry a negative charge if it can help it. So right off the bat, that's a little bit iffy. Okay. Let's try the oxygen on the left. Let's try that. Okay, so how many electrons are in a free oxygen? 6. Okay. All right, minus. How many lone pair electrons do we have? 2. Okay. How many bonding electrons do we have? Again, just like carbon, we have 2 in the double bond, so that's 4, plus a single bond, that's 6. So we're going to write half of 6. Okay. All right. So half of 6 is 3, plus 2 is 5. 6 minus 5 gives us a positive 1. All right. So not only is carbon taking a negative 1 charge, but oxygen, which is a very electronegative atom, is now taking a positive charge. So that's not good. That's definitely not good. Now, what's kind of nice is that the negative 1 and the positive 1 do balance out and gives us 0. So that is nice. But we are putting a positive 1 charge on an atom that doesn't want a positive charge. And we got a negative charge on an atom that would prefer a positive charge. So based on this structure is not correct. So we've got to draw another structure. All right. So what I'm going to do, let's go back to the drawing board. Let's try this again. All right. So the hydrogens were okay. One of these oxygens were okay too. It's really the carbon and the oxygen that are in the second and third positions. Those are the ones that we got to focus on. So what if we arrange this a little bit differently? Let's start with the oxygen or the hydrogen connected to the carbon. That was okay. Now, what if this carbon was actually connected to both oxygens? So what I'm going to do is put one oxygen on the top and then one oxygen on the right. And let's make the oxygen on the right connected to the hydrogen. So we're going to have something like this. Okay. So again, we started with 18 valence electrons. We've used up 2, 4, 6, 8 electrons drawing bonds. So that gives us 10 electrons left. Now we want to make sure that the outside electrons have octet. Hydrogens are good right now. So if we start with the oxygen on top and draw in the lone pairs, 2, 4, 6, that's good. For the oxygen on the right, we got 4 more electrons to put in. So we've actually used up all 10 electrons. So we got no valence electrons left. But both of those oxygens are now following octet. All right, so carbon, however, is not following octet. It's short 2 electrons. So what I'm going to do is actually take one of those electrons from the oxygen on the top, and let's use that to form a double bond. So in this case, here's what we got left. Let me draw in the lone pairs, and now everything is balanced. Now, here's where it gets good. Let's make sure, we have a potential solution again. Let's double check to make sure that this is an okay solution. So let's take a look at the carbon. Let's calculate the formal charge in that carbon. How many valence electrons are in a free atom? So you got 4 electrons. Okay. How many non-bonding electrons do you have this time? 0. So that's a big difference already. Okay. And then we want half of the bonding electrons. Well, in this case, carbon's got 4 bonds, 2 in a double bond and then 2 singles. So that's 8 electrons. So if we're going to take half of 8, which is 4, minus 4, that should give us 0. So already carbon has a formal charge of 0 in the structure, which is awesome. What if we try the oxygen on the top? Okay. So again, how many valence electrons are in a normal oxygen? 6. Okay. How many valence electrons do you have this time? You got 2 lone pairs, so that means you've got 4 electrons. Okay. How many bonding electrons do you have? 4. Half of that gives you 2. So half of 4 gives you 2, plus 4 would give you 6. 6 minus 6 gives you 0. And there we are. So in this case, carbon and the oxygens are also have formal charges of 0. And if you calculate the hydrogens and the other oxygen, that also should be at 0. So that's how you know you have a good Lewis structure. Let's try one more Lewis structure before we call it. So let's take a look at the nitrite ion, which is NO2 with a minus charge. Okay, so let's follow the pattern that we've been doing so far. Let's count up how many valence electrons you got this time. You're working with the nitrogen. You got 1 nitrogen times 5 valence electrons because it's in family 5A. So you got 5 electrons. Okay, oxygens, you got 2 of those. They're in family 6A, so they're going to have 6 valence electrons. So 2 times 6 will give you 12 electrons. All right. This case, you've got a negative charge, negative overall charge. So that means you've got 1 extra electron to add in. So that's going to change your number a little bit. So I'm going to add in, because of this negative charge, I know I'm going to have 1 extra electron. So 5 plus 12 gives you 17 plus 1. 1 more gives you 18 valence electrons. Okay. All right, so let's try this. All right, so which one goes in the middle? Because nitrogen wants 3 bonds, let's put nitrogen in the middle. We'll put the oxygens on either side. All right, so I'm going to draw 1 bond between both the nitrogen and both oxygens. So that uses up 2 bonds, or 4 electrons. So 18 minus 4 gives you 14 electrons left over. Okay, I'm going to make sure that each atom has octet first, and the outside, then we worry about nitrogen. So we'll put the lone pairs on the oxygens first. 2, 4, 6, 8, 10, 12. So we've used up 12 electrons for the oxygens. That gives us 2 electrons left over. And so we've got to put 2 electrons onto the nitrogen. All right, so that uses up all of the electrons that we're supposed to use. Perfect. All right, so now both oxygens have 3 lone pairs and 1 bond. So they're following octets. They're good. Nitrogen has 1 lone pair and 2 bonds. So it's got 6 valence electrons. We need an extra electron. We need another electron pair. So what I'm going to do is take 1 pair of electrons from the oxygen on the left and use that to form a double bond. So here's what we got. Nitrogen forms a double bond with the oxygen. So oxygen on the left has 2 lone pairs. The oxygen on the right still has that single bond, but it has 3 lone pairs. All right, so let's double check. Everything was following octet. The oxygen on the left has 2 bonds, or a double bond, so that's 4 electrons plus 2 lone pairs, that's 8. So that's still happy. Nitrogen has 3 bonds, that's 6, plus the lone pair, which is 8. So nitrogen is also following octet. Perfect. All right, so let's double check. Remember that if there's a way that we can verify whether or not this is a good structure, let's calculate the Lewis structure, or let's calculate the formal charge for that nitrogen. So let's double check that. So remember, for nitrogen, it's in family 5A, so it should have 5 valence electrons normal. Okay. How many non-bonding electrons does it have? 2. Okay. Now it has 6 electrons that are in bonds. So I'm going to take half of 6. Okay, so half of 6 gives us 3. That's not an equal sign, that's a minus. So half of 6 would be 3. 3 plus 2 gives you 5. 5 minus 5 gives you 0. So that charge on nitrogen is a 0. All right. Now, let's check the oxygen on the right this time. So let's try that. Okay. So again, you have 6 valence electrons in a free atom. In this case, you have 6 non-bonding electrons and 1 bonding electron, or 1 bond, so that means you're going to take half of 2. Well, half of 2 is 1. 6 plus 1 is 7. 6 minus 7 gives you a negative 1 charge. So that's where the negative charge is on your ion. So this is kind of cool. You can actually pinpoint which atom is going to carry the negative 1 charge. Very cool stuff. So this is a definite solution to the Lewis structure. So let me draw that out. Okay. All right. So that is a definite solution to the Lewis structure. Now, one thing before we go. In order to get to this Lewis structure, I took a pair of electrons from the oxygen on the left, and I used that to do a double bond. Couldn't I have done it this way? What if I did it with the other oxygen? So what if I did it this way? So here's where we were at. Okay. Here's where we were at. What if I take one of the lone pairs from the oxygen on the right and use that to form a double bond? So I have something like this. I form the double bond. This time it's on the right, and the single bond oxygen is going to be on the left. So that means that single bonded oxygen on the left is going to carry the negative charge. This, too, is also a definite solution because it gives you the nitrogen and the double bonded oxygen would give you formal charges of 0. The oxygen that's single bonded give you a -1 charge. That too is a definite solution to this structure. Okay, so this actually brings up another really important point in Lewis structures. And this thing, when you have two possible Lewis structures, the only difference between these two structures are the positions of the electrons. We call this resonance. So let's talk about resonance a little bit more. Okay, so we just looked at the nitrite ion and we said that the structure of nitrite could be one of these two structures, potential structures. One where the negative charge is on the oxygen on the right, the other where the negative charge is going to be on the oxygen on the left. Okay, so I said that they're equal. The atoms are positioned in the same way. The only difference is the electrons and where that negative charge is. Okay, so neither of these structures actually account for the bond lengths that we see in the nitrite ion. And it turns out that the bond lengths are going to be about 128 picometers. So they're going to be about halfway between a single and a double bond. So this is actually what we're talking about, this resonance, this idea of resonance. So these are resonance structures. Okay. Resonance structures are one of two or more structures for a single molecule that cannot be represented by one Lewis structure alone. Okay, so so that being said, if you've got two different Lewis structures, what does this molecule look like in nature? In order to answer that question, what's the actual picture of this molecule in nature? We actually have to combine all the different resonance structures to form something called a hybrid structure. Okay. All right, so the hybrid structure would be like this. This is going to be a combination of Lewis structures that gives us a better indication of what the molecule looks like in nature. All right, so that being said, what we want to do is try to figure out what is the hybrid structure of the nitrite ion. So we know, looking at these two structures, I'm going to cross out this letter A here because we're looking at nitrite instead of nitrogen, the ozone. We know that we got this. We've got an oxygen, nitrogen, oxygen. We know that there's at least a single bond between all of these, and the nitrogen has a lone pair, And we know that each oxygen has at least 2 lone pairs. Okay? Now we know that the double bond could form between nitrogen and either oxygen. Okay? So actually 1.5 bonds forms between oxygen and nitrogen. Okay? So we know that there's going to be at least one bond between them. I'm going to draw a dotted line between nitrogen and each oxygen to indicate that a half a bond could potentially form. Now, that being said, if that double bond is going to be split up into 2, that means the negative charge is also going to be split up to 2. So that means that negative charge is actually going to be a negative 1/2 charge, and it ends up being on both of the oxygens. So that would be potentially what we're looking for in nature, that we're looking for a molecule where nitrogen is bonded to 2 oxygens. It forms 1.5 bonds. Okay, so it's going to be the distance, the bond length for nitrogen oxygen is going to be between the distance of halfway between the distance between a single and a double bond. Okay, and the negative charge, the -1 charge, is going to be split up between both oxygens, and each oxygen is going to carry a piece. So this would be the potential hybrid structure for the nitrite ion.